Hi guys, this is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland, and this short video is going to consider the proof associated with showing that the square root of 2 is in fact an irrational number. And this particular proof is a proof by contradiction. But before we start the proof with respect to that, showing that the square root of 2 is irrational, there's a preliminary, I suppose, let's say, theorem or lemma that I require. Okay, so we have a preliminary, okay, let's say, a lemma, okay, that we require, and that particular lemma is something like this, okay. If a divides b, okay, so if we have some number that divides some other number, okay, if a divides b, well then a divides the square of b, or divides b squared. So what we'd just like to do is we just like to show this, yeah, okay. So let's show this, okay. So here's our quick proof, yeah, okay, of this particular fact, okay. Let's assume, okay, that a and b, okay, let's assume that a and b are integers, okay, okay. In other words, that a and b are elements of the integers, okay. So let's make that assumption, okay. So we're going to assume that a and b are integers, and that a divides b, okay. So we're going to make that assumption, okay. So if a divides b, well then we know from the division algorithm, yeah, okay. So from the division algorithm, the division algorithm, okay, there must be some number c, okay. So from the division algorithm, yeah, there exists some number c, okay, that's also an integer, okay, that's an element of z, such that b can be written as c times a, okay, because that's what it means for a number to divide another number, okay. If a divides b, well then b should be able to be written as the factor of two numbers where one of the numbers is a, okay, as a product of factors where one of the numbers is a, okay. So what are the consequences of this particular fact? Now we're assuming that a does divide b, so this must be true here. We must be able to find an integer c such that c times a is equal to b. Now what are the consequences of this? Well, if we square both sides, okay, so therefore we have b squared must be equal to c times a squared. Okay. Now what does this look like? Okay, so let's have a look at this particular thing here. Okay. So this means then that b squared, okay, must be equal to c times c, okay, or let's say it must be equal to c squared times a squared, okay. Or more importantly, okay, we must have that b squared, okay, is equal to c squared times a, okay. Now if we let c squared times a equal some other integer k, because c is an integer, its square is an integer, a is an integer, its square, its product with c squared must be an integer, so that means k must be an integer, okay. Well then what we've shown here is therefore, so this implies that b squared must be equal to k times a, which is the definition of divisibility, okay? Because what we've shown is that b squared is equal to some number, some integer times a. So therefore what we have now is that a divides b squared, okay? So this is an important lemma, okay? All it's saying is that if we have some number that divides some other number, if a divides b, well then a must divide the square of b, okay? So now we're ready to start the proof, okay, that the square root of 2 is in fact an irrational number. And the way we're going to do this is we're going to do it through contradiction, okay. So what we want to do is we want to prove, okay, that the square root of 2 is irrational, okay, okay. So to do this, here's the proof, okay. So the proof is pretty straightforward, okay. Once we accept the previous observation that if a number divides some number, if a divides b, well then that number must divide its square, okay. So here's the proof. So let's assume, okay, that the square root of 2 is rational, okay. So if the square root of 2 is rational, well then there exists, okay, an a and a b that are element of the integers. Okay, there exists an a and a b element of the integers, and actually it doesn't make any difference. Let's make them positive. Yeah, okay. There exists an a and a b that's an element of integers, such that the square root of 2 must be equal to a divided by b. Okay. And let's make another sort of assumption with respect to these a's and b's. Yeah, let's accept that this fraction, yeah, this rational number has been reduced down into its I suppose, let's say, more fundamental form where there's no common factors between a and b. And the way I'm going to say that is then there exists an a and b an element of z plus such that the square root of 2 can be written as a fraction. Okay, where let's say the GCD, the greatest common divisor of a and b must be equal to 1. So there's no common factors between them. Okay. So what's the consequences of this? If the square root of 2 is equal to a over b, well then the square of both sides, okay,